morning, everyone. My name's Paul Riseborough. I'm the author and maintainer of the NAV EKF libraries, a process which started in 2014, and they're still ongoing. We're into our third iteration at this point in time. And in the next hour, I'm going to run through some of the common faults that appear. Why did my copter fly vertically at high velocity and then come back down again? Why did it fly horizontal at high velocity and then go into a failsafe? Why didn't it arm? Why did my plane start to roll upside down? Some of these sorts of reports. So they all come back to sensor errors. In most cases, there are cases where there are some configuration faults that can be made. But before I go any further, I just wanted to draw your attention to the importance of IMU data in the EKF. Because people think the EKF is just taking all of this data and squashing it together, doing some mathematical magic, and if it's got a bad IMU, can't I just make it trust the barrow more, or trust the magnetometer more, or trust the GPS more? And the answer is, well, yes and no, and it's a big no, because I have here a block diagram of what EKF2 and EKF3 do. And you'll see here we have IMU and we have other sensors. All of the IMU data comes in, it gets downsampled, because we measure the IMU at a pretty high rate. All the other sensors also go into the EKF. They all go into buffers, and I'll talk about buffers a bit. But the most important thing to realise here is that the IMU data has a direct path into the EKF, goes straight through into what's called state prediction or inertial navigation system. And inertial navigation means you do integration. You integrate your gyro data, you integrate your accelerometer data. It's dead reckoning, which means your errors accumulate. If you get large errors, the angle, the velocity, the height, the position, it diverges very quickly, and the divergence, if the divergence is too great at too fast a rate, then the correction for those errors, which is what happens in this step here, using all that other data, which is hopefully being all brought together to be used at the correct point in time, so data needs to be time aligned, that correction is ineffective. And it doesn't matter what you do here, you can try to do magic here, but if this is bad, then it's unrecoverable. So that's the first point. The second point is that what the EKF is doing internally is it's actually not running at the current point in time. What it's trying to do, it actually stores data for a quarter of a second of data. Because all of your sensors have slightly different time delays. IMU is very fast. Magnetometer might be delayed by 50 milliseconds. GPS could be delayed by 150 milliseconds. Optical flow sensor could be 100. Your barrow pressure sensor has a delay in it. So we use these buffers, which we just store the data in the buffer along with a timestamp. It tells the EKF what's the measurement, what's the time of that measurement, including the delay. And then the EKF pulls the data out of the buffer, and when the timestamp reaches the same time as the IMU data it's using, so that it attempts to use data at a consistent point in time. That means for those of you that are integrating off-board sensors like SLAM or visual inertial odometry, or you might be integrating a different model of GPS, for example, if the timestamping is incorrect, it can have two effects. It can introduce errors, but if the timestamping error is very large, it can actually mean that the EKF will basically not use the data at all, because it never actually, the data gets overwritten in the buffer before the EKF gets to it. So that's a couple of points to bear in mind when you're thinking about quality of sensor data. The other point, which isn't so relevant here, but it also reinforces the importance of the IMU, is the EKF is running about a quarter of a second behind real time. So when you have a look at the EKF data in the logs and you're going, oh, hang on a bit, the roll angle on the EKF, it's delayed relative to the DCM roll angle, or it's delayed relative to something else in my data. The answer is yes, because it's running data that's coming out of a buffer. It stores about 1/4 of a second of data.
Is that by
If you've got it there, yeah. Mine's in my car. Drop the pen and then. All right, here we go. Oh, good. Does that show up on the video, by the way?
I don't know.
No idea. It doesn't matter. Oh.
Maybe, yes.
There we go.
Sure.
Okay. So we have this output predictor, and what that does, that takes the IMU data and basically does another inertial navigation system, and running the most recent data, so it's always up to date. And then it delays the output from that, compares it to the delayed output from the EKF, works out some errors, and then applies them back at the start. So the idea is that you've got this very recent movement using the most recent IMU data that basically always is corrected and follows the EKF. Okay, something to remember.
So
but once again, yes, sorry.
maximum lag we can have from the other sensors is 1/4 of a second, right?
Yes, that's the length of the buffer at the moment. That's what you can tolerate, up to 1/4 of a second of
So
delay.
if there's higher lag and the data is coming up, what will be?
It will end up, it will get to the data eventually, but the data, no, it will end up falling out of the window and then the data won't be used. The other way that you can make data not used is push data into this buffer so quickly that the data gets overwritten before it actually gets to the before it falls behind the time of the EKF is using it. So that's the other way you can muck things up. Throw data at the EKF buffers at a very high rate, and you can have the data
high rate, like faster than IMU.
Well, okay, at the moment, I think it's probably in excess of 20 hertz with the default parameter settings. I wouldn't go much above that, maybe 50 at tops. Now, you can make it's a one-line code modification to allow it to use data at the IMU rate. We can talk about that offline. But, so anyway, just to reinforce the importance of IMU data. All right. What's the EKF? I won't spend much time on this. It's essentially, it stands for Extended Kalman Filter. It's a mathematical technique that makes assumptions about errors on different sensors and tries to combine them in a statistically meaningful way. It basically does a prediction, tries to predict forward in time using the IMU data. It also tries to predict what the errors are. It's a big matrix which represents the errors, called the covariance matrix. It then gets observations from your barometer and your GPS and your magnetometer and your optical flow, and then it corrects the prediction from the inertial navigation system, and it also updates your estimate of the errors. There's a big matrix, won't say much more about it. All the terms along the diagonals, which we can actually get in the logs, they represent the RMS error squared. That's one way to think of it for each of the states. All the stuff up and the upper and lower or off diagonals here, they represent how much the error in one state or one variable is correlated to the other. For example, how much is the error in your north velocity correlated to the error in your east velocity? And that information is captured in these off-diagonal terms. We don't log these terms, so it's pretty irrelevant to log analysis, but just there for completeness. Okay, state prediction. Very quickly, it's a standard inertial navigation system. I just put it there so it's in the slides if you want to reference it. We take our IMU data at a very high rate. We might sample at 4 kilohertz. In the driver, it's integrated to form what's called a delta angle, which is just the little increment of rotation since the last update. And we did the same things with the accelerations. We integrate them at a high rate, and we get that little increment, little change in velocity since the last update. And then it goes through some processing using a very standard algorithm. Interestingly, it does rely on you knowing what gravity is, and we don't have a fancy gravity model. We just assume a constant gravity around the world. So our sensors aren't accurate enough for that to make a difference. Okay, and then just to say, when we get data from an IMU, we get measurements in degrees or radians per second, which is the rate of rotation of for example, of the gyroscope. What we do inside the driver for the sensor, remember the sensor is in the IMU driver, is we sample the IMU as fast as we can. I think we're running, 4 kilohertz sampling at the moment, 8 kilohertz sampling from memory. And then we essentially do a trapezoidal integration on that data, and we integrate these samples, and then we get the area under that curve is effectively the change in angle since the last time that you started integrating. And we call that a delta angle. And so the EKF doesn't get the data at 4 kilohertz. The EKF gets the data at, it might be, you get the data at 100 hertz or 200 or 300 hertz, whatever your main loop update rate is. And that contains the accumulated integrated angular rates, and it's called a delta angle. So got to remember the EKF, when it's internally, isn't using rates and accelerations directly. It's using delta angles and delta velocities, which are these short-term integrated quantities, the area under the curve. Okay. Now, before we go to log analysis, one of the most important concepts to understand with log analysis is something called an innovation, because that's what we'll be looking at. Now, we've covered back at the first slide how the EKF takes the IMU data, it does integration on the IMU data using a pretty standard algorithm to predict what's my attitude, roll, pitch and yaw, what's my velocity, what's my position. And that's a prediction. It gets a measurement from the GPS, or it gets a measurement from the magnetometer, and then it then says, okay, well, the inertial navigation system using the IMU data has predicted that my vertical velocity is 0.5 meters per second. But my GPS says it's 1 meter per second. There's a difference. There's always a difference. The difference is what we call an innovation. It's just think of innovation as the difference between what you get from integrating your IMU data since your last and what you're getting from your other measurements. It's a measure of consistency. So straight away you're going, we can look at those innovations, and they may tell us if we've got a problem with IMU data or if we've got a problem with other sensors. So what I'm going to cover in the next half an hour is how to look at these innovations, and it's not as direct as saying, I've got an innovation on down velocity, so therefore I have a faulty GPS. Unfortunately, it's not as simple as that. You've got to look at more than just one innovation to build a picture of what the errors are. Yes?
Why are they called innovations?
That went all the way back to one of the original papers for extended on the Kalman filter. You'd have to ask the original authors why they decided to call them innovations. It's just a term that's stuck with the Kalman filter since the 1960s. Yeah.
Was it fun?
What? Was I alive then? That's a rude question. Yeah. You can guess. Okay, so. And a couple of things there. And look, I've just given you some examples here of some GPS velocity innovations, and here I've shown the bounds, which are where the filter expected them to sit within. And you can see these are the innovations for a normal flight when it was hovering and then it was doing some flying around. And they're supposed to be zero mean, hovering around about zero with a bit of noise, and the noise should be within the limits expected by the EKF. And there are parameters which you can use to tune the EKF to make it expect more or less noise from the sensor. Okay, I'm not going to cover EKF tuning in this presentation. I'm not going to cover that. That's the overview. I'm just throwing that in the notes for people that are actually interested in the states and the derivation. So now we go on to the log analysis. Okay, I have just loaded a log kindly provided by Peter Barker, because he informed me that he had a Bixler, a plane, that had the worst vibration at CMAC? Or somebody else? Measured vibration, yeah. Listen, the ability to send the EKF ballistic with certain combinations of throttle. Okay, so now this is actually something you see with new setups, particularly because a user will go in with a new setup and they don't know what the vibration environment is. It's complicated. You can have a carbon airframe, and if the propellers hit a resonance on that airframe, the vibration levels can go to 16, 20 Gs or above. Okay, so here's an example. So what's the first place you go to when you're looking at a log? Well, I go to these things called, people call them variances, probably not a very good name. They're actually, we have here, it's an overview of the innovations. It's a measure of, we take the magnitude of the innovations for all of the GPS, or the GPS velocity, or the position, or the barometer for the height, velocity, position, height, or M for magnetometer, or VT for true airspeed. And these are available in Mission Planner. So I'm using MavProxy here because that's what I'm familiar with, but these variable names are available in MavProxy. And Michael, I believe, says there's a way to actually set up these plots, these combined plots, which are available in MavProxy and now are also available in Mission Planner, which you access by.
There's a drop-down list in the log browser screen.
Yeah, the drop-down list in the log browser screen. Okay, so you can get these plots. And the plot concerned, the first one you go to. This is the go-to plot. Go to EKF. And these are normalised innovations, EKF2. Now, they're normalised because anything over 1 means the EKF has failed that sensor and is refusing to use it. And, well, I'm sorry, Peter, but you've managed to hit almost 35 there. That's pretty good. Oh, that's very good. That's a high score. However, mere mortals usually manage to just get things up to about 2 or 3, all right? Setups. So here I've zoomed in. It's not. We'll have a look at the vibration data later. But so the first thing to look at is, okay, let's have a look at what innovations are climbing very rapidly and are failing. Well, here I've got blue and I've got red, so I've got velocity's failing and height is failing. Now, that's one of the big giveaways for a vibration that's affecting the vertical accelerometer. And Randy and I have been having a discussion. I think we're about to end up with a pull request shortly that will make the vehicle self-recover from that type of error, detect it and then I won't say eliminate the error, but will prevent the vehicle gaining, 150 metres of height if you're a copter. Because what happens when you have clipping on your vertical accelerometer is the accelerometer is measuring 1G. When it starts to clip, instead of measuring 1G, it squeezes the average acceleration measured towards 0, right? So the accelerometer is measuring 1G, or it measures minus 1G because positive is down with the accelerometer. You put a lot of vibration in and it squeezes it starts to clip. It squeezes the average value to 0. This is such an important concept. I'm going to put a whiteboard in front of the camera here, or can you just swivel it?
I can just swivel it.
Swivel it around, that's good. Okay, so we have acceleration in the Z direction, and remember that Z is down. So it's measuring minus 9.8, there and thereabouts, plus a bit of movement of the copter. It's just like that. Now I'm going to pretend I've got a sensor that can only go between +1, so it can only measure between -2 and +2.
I think it's a permanent marker.
Is that a permanent marker?
It's very important information.
Yeah. Yeah, all right. This is great. Okay. So plus 9.8. Let's say plus 20, and this one's minus 20.
Yeah.
And then let's say we've got something that saturates at those levels. You can get rid of that by writing over the top of it.
You can see how well that worked on the other side of the board.
Yeah. Now, so I've got a signal like this, and I've got noise. So let's imagine we've got a sensor where it's actually limited to plus. It's got a dynamic range of 2 Gs, which obviously we don't, but it's going to make it a lot easier to draw. Now, I've got a little bit of vibration. What happens as I start to throw this thing into saturation, I have a measurement down here and a measurement up here and a measurement down here, is that it ends up flipping. And what you end up getting is measurement, 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 measurement. In other words, your measurements are basically starting to sit, most of your measurements are starting to sit at your clip limits, which is symmetric around about 0. So what happens is you throw a huge amount of vibration at your vertical accelerometer is that the average value starts to tend towards 0. Now, how do you measure a 0 accelerometer value? Under what condition do you get a 0 accelerometer value?
Free fall.
Free fall. So the INET, so the inertial navigation system goes, I'm free falling. And then the EKF updates come in and going, oh, well, sorry, Barrow disagrees and GPS disagrees. But it continues, and then eventually it goes, well, the Barrow and the GPS are now outside the innovation limits. It stops using the Barrow, stops using the GPS. The height control loop ramps up to full throttle, trying to stop it free falling, which immediately makes the vibration worse, and the copter accelerates into the air at very rapidly. Now, eventually the EKF will then do a reset, and then it'll come down again, and then it'll keep on repeating the process over and over again. And that's what we see in this log here. Now, fortunately, this vehicle was not in a mode where it was using height, or else it would have been a very interesting flight. So you'll see this characteristic behaviour where the vertical velocity. So we go, I'm going to graph the innovations for the vertical velocity. So NKF3, so if you're looking for innovations, you need to go to NKF3 on your mission planner. Sorry?
That's not bad.
It's not going to work. That would be fun, wouldn't it? NKF3 dot I.
Troubleshoot plus.
Troubleshoot plus.
There you go.
There you go. I think that'll do it. Yeah. And I'll zoom in. Okay, so we can have a look at where the first divergence happens. In fact, so you can see the vertical velocity innovation is bad right at the start. Now you can see that the innovations here go positive, and this is a very important characteristic when you get this vibration. What's happening before it diverges is you'll see that both the vertical velocity innovation and the vertical position innovation are positive. When you see they're positive and the EKF goes into an uncontrollable, it basically loses use. It basically starts rejecting the GPS velocity, it starts rejecting the Barrow, and these innovations are positive. That is nearly always, like 99% of the time, that is clipping. Okay. So I just thought I'd throw that log in there. We won't do too much more on this log because other than the vibration. And the other characteristic you'll see is that after it's been climbing ballistically for about 10 seconds, it then does a reset. And then the process keeps on continuing. So you end up with these series of climbs. And unless somebody's able to fly in a non-height controlled mode, it usually results in loss of vehicle.
Paul, is there any
Yeah.
way of telling what sensors are no longer being fused?
Yes. A couple of ways to tell. One is that if you looked at the normalized innovations, which are these NKF4, so you'll see NKF4.SV. Apologies for I can't make that larger on this plot, I don't think. Tridge?
So which one do you have?
These, I can't make this legend or this
No,
yeah.
unfortunately
Yeah.
not. You'd have to
Yeah.
zoom in your screen. If you do Control Alt Plus, you might be able to zoom the whole screen, or you might lose the screen completely.
Okay, I'll carry on. Okay.
Very close.
If these normalized innovations are the ratio of the magnitude of the innovation and the level at which the maximum level that the EKF will accept and still use the data. So it's above 1, it's a fail. And we also show on Mission Planner, we've actually got the little bars that show the values of these normalized innovations. And I think we've got green is below 0.5.
Yeah, 0.5 to 0.8.
Yeah, and then we go amber from 0.5 to 0.8, and then we go red above 0.8. Yeah. Okay, so let's go on to a log with a bad compass. Strange logs, yes. Now this was a log that Randy sent me. This was somebody that was flying the vehicle. They were flying near power lines at the time, and that may have been a contributing factor, but there's certainly more that's going on in this log than that. So first of all, the description was that the vehicle was flying near the power lines. It started flying in random directions horizontally, and eventually it recovered. Gave the operator quite a fright, because I think these were high tension lines, weren't they? Yeah. And there is evidence of some magnetic of noise on the magnetometer. So the first thing is to look at these pre-packaged graphs. So once again, we go down to normalized innovations for EKF2. And I'll just zoom in. And these are the NKF, these are the values in NKF4. And once again, what's to note there, that V stands for velocity, which is your GPS velocity. P is position, that's your GPS position. H is for height, that's whatever you've selected as your height. It could have been rangefinder, but in 99% of cases it's baro. And then M is essentially your magnetometer. And then we've got SVT, which is velocity T for true airspeed, but that's which is only applicable for planes. And then you'll notice that these are repeated, and they're repeated again for the second EKF. Now the reason we plot all of these is because if I have an error and it appears on both EKFs, then it's highly unlikely that it's an IMU fault. Here we see evidence of these normalized innovations have gone above 1, and I go, well, that's interesting. So straight away they're above 1. That would have been should have been a red light or a red event on the ground station. And normally, as an operator, if you saw that, that really should trigger a, do you want to RTL? In this instance, I think because the flight was in Lauter at the time, and they're looking at the copter, they're not looking at the ground station. We don't have any haptics or any sort of feedback to the operator on most systems for these types of errors. So you can see here that both the GPS velocity on errors on both IMU, both EKFs, went high at a point in time in flight. Well, that's of interest. Now, that normally doesn't happen. That could be two causes. It could be a glitch on the GPS. So what we do when we have a look at a glitch on the best way to tell if you've got a velocity error on your GPS is to have a look at the vertical velocity of the GPS. Because if the GPS glitches, the vertical velocity will glitch. And in fact, it will glitch more than the horizontal velocity. And the great thing about vertical velocity is that we've got another source that tells us whether it's just vertical velocity in the GPS or if it's something to do with the IMU. And that is, we've got baro. Because we have three sources that give us a measurement of vertical velocity, of vertical motion. We have an IMU, we have a barometer, and we have a GPS. So the first step here, is this a GPS glitch or is this something else? Let's have a look at the innovations for everything that contributes to the vertical velocity measurement of the vehicle. So we go graph EKF 3.IVD. So I want to have, okay, what's happening to the vertical velocity innovation from the GPS? Just look at the vertical channel and EKF 3.IPD, which is the innovation for the barometer. And in that instance, we can see that this was a GPS glitch. Yes.
I usually check the GPA message first, which gives you whether the GPS.
Well, okay, so this is looking at the output data, right? And this is evidence that did a glitch. Now, you can have a look at the GPA because we can graph the GPA, and that's what the GPS reports. But if there's multipath, it doesn't always report a. But sometimes, often it does. So we can look at GPA dot. Now the GPS has a measure of velocity. Of velocity error? No. Yeah. It's capital uppercase O. Yep. And here we can see that the GPS was reporting, this GPS doesn't put out our speed accuracy.
Go back to the full zoom. Is it the same time for time?
Yeah.
No, just
Now look at this, 015147.
Yeah.
And then 015147.
Yeah.
There you go.
Slow.
Yeah. Look at that. So, see, not all of our GPSs produce that data. U-blocks do,
Yeah.
but other drivers don't, unfortunately. You might be able to infer it by looking at the position, but that's usually a position reported accuracy, but that's pretty lagged. But in terms of just looking at the data rather than what the GPS says it's doing, I say, well, hang on a bit. Here, the GPS is jumped by 6 meters per second for a short period of time. Now, that's a caution in a flight because that tells you if the GPS has done it once, can it do it again? So now immediately the GPS is on the suspect list. So now we zoom out and we go, well, okay, well, this wasn't the bit that scared the operator. The bit that really freaked the operator out was this part here because you can see it went into RTL. So let's have a look what happens here. We have another divergence.
Isn't that just after the operator's been freaked out? Isn't that?
No, okay, so here we go. It's diverged. It started to diverge here, and now it's gone into RTL. Now, did the copter start to wander? By the time you get to about 0.8 or 1, the copter's clearly doing something. So we've had 2 consecutive events. On the first event, the operator didn't respond, left it in loiter. On this second event, the operator's reacted and put it into RTL. And so now we can have a look at some of these other graphs and go, what's happening here? Well, at this point in time, we've got the baro innovation. Baro innovations aren't great, they go up, but you can see once again that the vertical GPS innovation jumps. So in this instance, this looks like we got an issue with a GPS that is actually glitching. Now, something else that can cause loss of horizontal position, and typically it can be either a GPS glitch, The other contributing factor, which is quite common, is magnetometer. And I'll explain why does the magnetometer matter? Why is your angle important? It's because let's do a thought experiment. What if the EKF thought that the vehicle was pointing, or the inertial navigation system thought that the vehicle was pointing east, but in actual fact it was pointing north? The vehicle starts to move in the east direction. The GPS says, oh, you're moving, you've got an east velocity. However, the inertial nav system thinks, well, I'm pointing east. It sees that movement and it interprets it as a movement to the south. In other words, the inertial navigation system will take its dead reckoning of the accelerations, and they're going to be rotated by 90 degrees. So the inertial navigation system will think that the vehicle's moved south. The vehicle moved east. The GPS says it's moved east. The inertial navigation says it's moved south. The EKF's looking at this big inconsistency. If it's large enough, it will say, all right, well, I reject the GPS, and then 10 seconds later, I'll try to do a reset. Whereas the root cause could have been the fact that the yaw was out by 90 degrees. This is a severe error. This is something that we have protection for in the Copter code. If you take off and you enter this condition, we have what's called an EKF failsafe, and that will be triggered by large innovations, rejection of the GPS, and then it will go into, I think the default is land mode. Yeah. Now, what are the signs of a bad magnetometer? Well, it's not as simple as saying, oh, let's just look at the magnetometer innovations, and if they're high, we have a bad magnetometer, because that may not necessarily be the case. Because the magnetometer could be rotated by 90 degrees in the airframe, for example. That's less likely now with the changes to the magnetometer calibration. In that case, the magnetometer data will be completely consistent with what the EKF thinks the heading is. The inconsistency will appear when you try using the GPS data. So we've got another graph here that shows what happens with bad magnetometers. Got an offset failure. Oh, we've got a. Oh, that's the bad mag, but that ended up being. Yeah, that's. Yeah, I open up that log. I think that's the same log we looked at before, but this also had a second problem which was related to magnetometer, not just GPS. There were two things going on with that log. And that's often the case. It's often not as simple as one thing. The EKF can tolerate one error, but sometimes you see a log where the magnetometer hasn't been calibrated correctly, or it's got interference. The GPS is noisy and been interfered with, and there's high vibration. And you put all of those together, and it may work on ground testing. It gets into flight, and then 15 seconds later, it's all over. So we have progressively improved the way that the user is notified with these errors, but there's still some areas that we can improve. Okay, so if I'm looking for evidence of problems with the magnetometer, we have a pre-packaged graph here under sensors. We go to compass, and you need to make sure that you're actually using the compass that you think you're using. So, and I've been caught out this way, looking at a log provided online with an extensive analysis, and then somebody's pointed out to me, oh, by the way, they were using the other compass. So, in this case, you can check the parameters in the log. And here we can see right at the bottom that compass they're using compass 1 and compass 3. Now, it should be defaulting to compass 1.
Compass primary is 2.
Primary is 2? Oh, there you go. So it's defaulting to 2.
Isn't being used.
Yeah.
Yeah.
Command dev ID.
That's right, yes. So in this case, they've selected the primary to be 2, but 2 is actually deselected.
Pretty sure compass is actually off.
Yeah.
This might count from 0.
Now,
So I've had that problem.
and so this is the question. In this instance, what compass is this log using?
Yeah. Type the command dev ID.
Um,
DEVID, all one word. that says what the compasses are. You widen that a little bit.
Yeah.
So you can see the first one was an SPI. The third one, which is number 2, is UAV CAM.
Yeah, compass primary too is actually the third compass.
Yes. So he's basically set the compass primary as the CAM compass.
Yes.
And it is enabled because use 3 is 1.
So in that case, yeah. Did you get all of that?
Multiplied by pi.
So now when you're looking at this compass, we need to plot compass 3. So we go to graphs, sensors, compass. Let's have a look at compass 3. Now, one of the things to look at when you have a look at a graph of the compass is if you just look at the individual components of the compass, which are the X, Y, and Z there, it's kind of hard to make anything out from that. You can tell if they're very noisy. If you're experienced with looking at logs, I like to look at the magnitude of the magnetic field strength, because if you have a magnetometer that's been perfectly calibrated and free from interference from electromagnetism with your propulsion system, then this will be a straight line. It'll be constant. You can see here that we have some variation in the magnetometer, but usually anything less than plus or minus, anything less than a range of a variation of 50, which you've got here, that's normal. This is acceptable in terms of magnetic interference. It's around about 10% of the field strength. That's an acceptable value. You can go up to as high as 15% field strength before you start to see issues with maybe slight toilet bowling. I would, if it was my airframe, I would probably work on improving that, but you wouldn't look at that and say that was a cause of a loss of navigation. So in this particular log, although it was tagged, initially the observation was, we think it's might be an issue with the compass, and that was causing it. It was using the wrong compass, and because of the confusion with the compass use. In this case, as we saw before, the real cause of loss of navigation was the problem with the GPS.
Sorry, in the graph, what drives the background colour? Pink, green.
Flight mode. So on Map Explorer, it'll colours it in. So you can see down here we've got the loiter. Yeah. So that's one of the first checks to do. If you're trying to work out, do I have a problem with my calibration, or do I have a problem with my magnetic interference from the motors? Just plot the magnitude of the field strength, and we've got those combined plots available also in Map Explorer. There's another thing that you can look for evidence of a problem with magnetometer rotation. If you have an inconsistency. Now I have one log here where the magnetometer, where we actually had, I've got one log here where one of the IMUs was actually rotated incorrectly on the board, which is a very interesting log. All right. Yes, this was a very interesting log.
It's rare.
It's rare. Yeah.
It's rare in how we can do auto orientation.
So let's have a look at the EKF. So straight away, our go-to plot is always these normalized innovations. Now this was a very unhappy flight computer. There's a lot going on here. Well, straight away, before it stabilise, you can see that we've got the magnetometer innovations. It's failing the magnetometer. It's failing on the magnetometer on IMU 2 was failed right from the start. And then we'll show you the vehicle does a rotation, and then the next magnetometer is failing. So that's a clue immediately. And you'll notice that this magnetometer is failing, then it passes, then the other magnetometer fails. Now, what does the user do to go between a failure on the magnetometer on EKF2, on the second EKF, to a failure on the first EKF? The answer is they just did a yaw rotation. No, they didn't do a yaw rotation. So now we've got a magnetometer that's failed and come good, another one that's been good and failed, and the user hasn't rotated in yaw. Oh, there we go. So how do we resolve that? Well, let's have a look at the magnetic field strength. Well, let's check what compasses they're actually using first. They're using compass 1, and the primary is set to 0, which basically means default to the first instance. So they are using compass 1. So let's have a look at the at compass 1. Sensors. We've got compass. Yeah, okay. Okay, so what do they do to make one magnetometer? One magnetometer was failing on the ground, right? And then it started to pass, and then the other one was passing, and then it started to fail, right? Well, one EKF was failing and then passed, the other one was passing and then failed, rejecting the magnetometer. And it happened at a particular point in time, and the point in time that it happened is, well, it's got nothing to do with your rotation, but there was an event. There has to be something that's changed. What changed? They did a takeoff. And I'll show you the throttle. Now, we talked before about the importance of having a consistent magnetic field strength. If the magnetic field strength isn't constant, that's an indication of a problem with either calibration or magnetic interference. We talked about how anything over more than about a 15% variation, and I'd be pretty uncomfortable with, calling it a reliable setup. Here, we have a variation. It went from just over 500, and in flight it's going up to 1,000. So that's a 100% change in magnetic field strength. So at that point in time, you don't really need to dig too much further into this log to say, well, why did this thing, well, first of all, this is a major, and at this point in time, you'd be justified in saying, well, that's what caused your crash. Fix your compass interference, calibrate it, fly your quadcopter again, and it'll be right. Well, turn on and checks on. Oh, yeah, this was a good, yeah. Were they on? I bet they're off. They have to be off. Are they?
It's also done use 2, use 3 off. It's got some on.
Some. Oh, I don't know what 6606 works out to in terms of what's been.
Decoder.
Yeah, that's right.
I'm pretty sure the IMU checks it off.
Yes. Now the yeah. Now that would make sense because that's turned off, and I'm inconsistency error. Because
Does that compass on?
He's got compass on.
Barrow compass.
Yep.
Oh no, 60. That's decimal. Sorry.
Decimal. Yeah. What's he turned off?
So he's got CE. He's actually got what's 19 CE hex, which means he's got Barrow compass, GPS, INS. He's got most things on. Yeah, so 19.
Just turn the one that is off.
He's turned off things like airspeed, logging is turned off.
Nice, that's innocuous.
Yeah, but most things are on.
All right. Now, what we do now is we're going to zoom into the flight terminating event. Yeah, okay.
That's a big gyro.
That's radians per second. All right. Now, first of all, I looked at that and thought, well, the diros, they agree. And then it was a, hang on a bit. So what have I got here? Let's zoom in and have a look at the differences. Yellow is IMU3 gyro Y. Black is IMU2 gyro. Hang on a bit. Is that right? That can't be right. No, we got green, and green is IMU gyro Y. But where's IMU2 gyro Y? I can't find IMU2 gyro Y. Oh, hang on. IMU2 gyro Y is down here. So it wasn't me that worked this out on thread. It was worked out that the IMU was on the board was rotated by 90 degrees. Now, so this is what happened with this sequence of events. Copter takes off with absolutely ridiculous levels of magnetometer interference. It's failing. EKF1, first instance of EKF fails, second instance of EKF2 fails. They're failing alternately depending on what orientation the copter's at. And because it tended to hover at this point in time. At some point in time, the IMU1 EKF fails. The IMU2 EKF is momentarily healthy. It switches to the IMU2 EKF, which has got the rotated IMU, and then the copter immediately just flips onto its back. And that was the failure mode. So it was more than one thing, yeah.
How's that possible?
Would DCM have saved it?
Depends on what IMU it was running on. If it was running on
How is it
IMU2.
possible to have the IMU data upside down?
Well, just do messages space COP. Messages space COP for copter. Okay, we see that it's ArduCopter 3.6.5.
Yep.
And param BRD underscore T type board type. See what type of board it is.
Looks like a cube.
No, that's not a cube.
Board star. And board type is 3, so it's identifying as a cube type. We sometimes get problem having the board type wrong.
Oh, we get that all the time, especially when they
Yeah.
copy and hold parameter batch. Well, the dev ID is that 1 to a pixel. 2.
So
Dev ID should be able to,
Oh, we
you get board time, the actual board time.
You know what this board is.
which one was
This was, I believe this was a very old CUAV board.
Uh-huh.
Oh, was it a Pix hack, was it?
It's a Pixhack V3, I think.
Yeah.
And the user reported that they had a batch of them. They had 3 of them or something that had this problem. But
Yes.
it was an old.
I've got one of those boards
Yes.
was correct.
Yes, you tested yours and it was fine.
So it might have
Yes.
been an early prototype that had
Yes,
the
that's
different
right.
configuration.
Yes.
Exactly, that's our test.
Yeah.
Have had problems sometimes with the power on sequence of some IMUs and coming up rotated. If the power comes up wrong, we had that in the very early days. We saw one with it's LSM3 and 3D, I think it might have been. One of them
We
occasionally.
added a whole, like a hardware fix to that.
That's right, being able to control the power on the sensor rail. But we did have at one point IMUs coming up. We also had compasses coming up rotated by 90 degrees
Yeah.
with a bad power on.
So
Now-
the question on that is that we only check the primary EKF for failure. So your secondary port can be totally failed.
All right.
Take off.
No, Randy's now fixed that.
Yeah, let's fix that.
We'll
Now,
now check for that now.
by the way, have a look, and when you can see what happened here, and this is what was very interesting. So, if you want to know which core is being used in a multi-core setup, you go to EKF4.pi, it stands for primary instance. And you said start out at 0, which is your default EKF, the first one. And at some point in flight, it's shortly after takeoff, it's looked at the error and gone, that EKF is performing very badly. I'm going to switch to the second one. I don't think that was the one that wasn't, which one he was using. That was obviously not rotated because it continued to fly. That instance. This is what got me a bit confused looking at the log, but
Just as it took off.
just as it took off, yeah. Now it's flying on that EKF, and at some point in time that gets unhappy because of the magnetometer errors. And then it switched to the first instance, and then it rolled upside down. And the question was, well, why did it select the wrong EKF? It selected the one that was momentarily healthy. So,
That's got to be a pretty odd long run with a
Yeah.
Manage your IMU actually upside down. I mean, that's a pretty serious hardware.
That is a serious hardware fault. What it does point out, though, is that it's a good example of a lane switching event, and it's a great example of a very high level of magnetometer interference.
We're going to get it more often as we start having CAN IMUs. Because then
Assuming we decide to use them, I mean,
yeah. But if we start doing CAN IMUs, it's going to be more common for people to do it.
Should we add the ability to actually force it to change lanes so that it can actually test on the ground?
or should we do a startup where we actually change lanes to verify?
Which is what I'm going on.
You can certainly test the different IMUs by changing the IMU mask to only use the IMU that you want to test.
Yeah, but I'm thinking about a. Yeah, I think that there's certainly something that could be done better in terms of startup checks on the second lane.
Do a calibration with shape your property. All the IOUs agree.
Okay.
It's hard to check your IMUs though when they're all stationary.
And only the gyro was off, not the accels.
Yes, and it was stationary on the ground, so it was fine. Yeah.
Mind you, if they'd had IMU used at the 7 on that, would it have fallen over to the third one, which was set correctly?
Right. Yeah.
Only if it's unhealthy data.
Here's a question for you, Paul. With the multiple GPS users, multiple magnetometer use, use these magnetometers. How's the magnetometer data split up, either in each EKF or among EKFs?
No,
it's a fallover, right?
No, yeah, okay, so what the EKF will do, it will use the first magnetometer instance, primary instance, continue to use that. If the magnetometer has been rejected for more than, I can't remember the time period, it will eventually, will switch over and attempt to use the next magnetometer. And then it just keeps cycling through the list. Now, this was causing a problem. There was a bug that was fixed where it would cycle through and end up trying using a magnetometer that wasn't there, as in no magnetometer. So we had one log. That was fixed. That went into master probably within the last month.
Yeah, and that's been released as well.
Yeah. Yeah, that's.
Well, it actually where it would have tried to use the next one, but switch back to the
first one. Yeah. Yeah, because that instance it tried to use wasn't there. So yeah. Okay, so this was an interesting log that I thought initially was caused by engine vibration. So the description was that the vehicle started to climb uncontrollably. That was the user's description. It was a bit of a wild ride because they went into, it was flying in auto quite happily. Suddenly it starts to climb uncontrollably. Well, it wasn't a ballistic climb, but it was certainly gaining height on the auto mission. They went RTL, then they tried to land it, RTL, back into loiter, tried a few different options to try and recover it, and eventually the vehicle, I think it drifted into a tree, or I think it was they lost. Yeah.
So it's a really good reason to have stabilize on your utility list.
Yeah.
Control.
That's right.
Stabilize is not one of the modes that they selected in that little.
All right. So, this was an interesting log, and the reason I've got this log in here is because it illustrates how the current method of doing failover between EKFs is not foolproof. Because an EKF is classified as failed if the normalised innovation goes over 1. Now you'll notice here that the velocity innovation and the barometer innovation levels, normalised levels, don't get to 1. So it continued to use those sensors, but the output, the vertical velocity and the vertical position is incorrect, and that caused the vehicle to gain height. You notice that it only affects one EKF, it doesn't affect the second one. So in other words, it's on one IMU and not the other. Now when you see that, it's a fault that appears on the EKF that uses IMU1 and not the EKF that's using the second instance of the IMU, then that's a pretty good clue that there's something going on with the IMU data. Unfortunately, in this case, the user had turned off IMU logging. which was inconvenient. So, okay, so what are the other clues there? Well, let's have a look at the innovations for both not just the magnitude, the normalised innovations. Let's have a look at the actual innovations in engineering units of metres and metres per second. So we go graph NKF 3.IVD, and then we do NKF 3.IPD. We pull those up, and yeah, they're both positive. Now, when I saw that, my first reaction was, that's vibration, and it's just affecting one IMU. But the vibe, then I had to look at the vibe levels. Graph VIBE dot, I'll look at Z. The vibe levels look low, up to the point where it hits something. And then I can do clip. There's no evidence of clipping up to the point where it hits something. That's a gain.
Is that the white mode? That's after you hit something, that's the mode you go into. That's the mode you get.
Yeah. Apparently, flying into an object, it tends to fire off the clip indicator.
Crash and disarm.
So what do you do then? You've got something. It's appeared on one EKF. It doesn't appear on the other. So let's have a look at the vertical biases, because the EKF tries to estimate the offset in the accelerometers. It's in strange units, but graph NKF 2.AZ bias, and I'll do the second instance of the EKF, NKF 7.AZ F6, yep. No, NKF, yep, 7.AZ bias, yep. All right. Well, look what happens. I think these are in centimetres per second squared, the units. So they're trying to economise on use of log data and sent down as an integer, or logged as an integer. So here's the second IMU, and it's slowly adjusting throughout the flight, which is typical for something that's warming up. You see these sort of drifts in bias values, but you get this sudden ramp up in bias. The EKF is trying to learning and compensating for an offset in the Z accelerometer. And this is also consistent with when we have a look at the innovation readings. We can see that they start off large, and then towards the end of flight they're slowly coming down as the EKF's learning that offset. So all we can infer from this data is that for some reason that sensor axis developed an offset, a sudden step change in offset mid-flight.
Just came unstuck.
I don't know.
May I ask what sensor?
I knew you were going to ask that.
He doesn't care what, he cares who. It's his or someone else's.
I care what. Lots of sensors. Everyone basically uses.
It's the first one,
The first one.
first accelerometer.
Yeah.
So that's SPI2, it's a MPU 6000.
Is it? INSAC.
That's two.
Yes,
It's
and
the
that's the first one.
MPU
Yeah.
6000. Unfortunately, we also mapped one of the ICMs onto MPU 6000. We didn't differentiate the same driver.
That's only for compass, isn't it?
No, we do that with one of the others. Most
Looking-
of the ICMs are broken out. There are two types that map
Yeah.
to MPU 6000. Plus 6050 is mapped to the same.
Yeah. That's, yeah. So, I mean, these are rare occurrences, but they're not unknown.
Yeah.
And this is why we want to move towards one of the things about going to the F7s or H7s with a bit more grunt, or particularly a bit more memory, is that we can basically run an EKFs on matrix combinations of sensors and then do a median select on the output from the estimators. So we're no longer relying on, well, I've got two estimators, I'm going to pick them based on this one's going to be primary, and if it goes above this threshold, I'm going to move across. Because then you're in the business of selecting thresholds. If you select the thresholds too high, then this happens, what you saw in this log. The vehicle was pretty much unflyable, clearly, but yet it wasn't quite large enough to trigger the threshold. If I set the thresholds lower, then we'll be getting in-flight switches between lanes and vehicles sort of, that will cause other issues with users, false positives. The median select algorithm or method is a more reliable way of doing it, but we do need the extra RAM and the extra footprint to be able to do that.
Yeah, so that's a Pixel 1 or a clone.
I think that's a Pixel 1 or a clone, yeah, based on the sensor fit. Yeah.
I suppose in that case, exactly, the second IMU was actually doing a nice job.
Yes.
So, yeah, we've got to talk about it. Obviously, a bit hard to do median select between two, but
Yep.
when you've got a few more and running the extra mixed EKFs, then you get quite a nice start.
Yeah.
And you potentially work with some median select.
So it would be nice to have that dev ID.
So median select, you mean run at least 3,
Yes.
choose the one.
Take the middle.
No,
Yeah.
I was on him on that one early.
Or if it's an even number, take the middle two and average them. Yeah.
Take the middle.
Yeah. Anyway, so I'm truly out of time. I think that's it for the log analysis. Are there any specific questions there?
I guess a small question. What does it mean when the innovation is negative?
Okay, so innovation is the estimate, is the prediction minus the measurement, right? Okay, prediction minus measurement. So if my inertial navigation system is saying that I have a vertical position of 50 meters, and remember down is positive, okay? So thought experiment, the flight vehicle's at ground level, 0. The inertial navigation system thinks it's falling rapidly. So it says, oh, I've got a vertical position of plus 50, which is down. And the GPS or the barometer is saying you're at 0. Well, the innovation is the prediction from the INS, which is plus 50, minus the measurement from the baro, which is 0, so that's a positive value. So wherever you see a positive innovation on the vertical velocity or vertical position, it indicates that the inertial navigation system is falling, dropping relative to the other two measurements. And that's the characteristic sign of clipping. Yeah.
Positive and negative.
Sorry?
Negative, it's very bad.
It's going up. The inertial, the inertial navigation system is rising. That's actually quite rare.
You want to analyze a lot with positive.
You've got one where both innovations are negative. Oh, I'd like to see that afterwards.
You still have the log at Fort Worth International on the solo. That the log just sort of keeps going until it hits 4,500 feet.
So the question is, do I have the log from a solo log from Fort Worth where the vehicle
disappeared into the international flight path of the international airport for 4,500 feet?
I have no knowledge of that event.
There's still a reward of $200 out for the recovery of that vehicle.
Yes, Tom.
What are the benefits of going to floating double precision?
Yeah. Okay. So the question was, what are the benefits of going to double precision? Double precision would open up the ability to either add more states to the EKF and still maintain without the risk of running into numerical instability with the matrix, with the operations due to loss of precision, or it also enables us to go to a tightly coupled integration with the GPS where we can move to an Earth-centered, Earth-fixed reference frame and end up fusing in the range measurements from the GPS. That's another possibility. And
that sounds useful.
Yes, it's a decent amount of work.
When you say the range measurement from the GPS?
Okay, so the GPS puts out delta range measurements. And you know whether you use the ephemeris data to work out the position of the GPS.
Mm-hmm.
So you've got the orbital mechanics model that goes into your prediction model. You know where the GPS was when it sent the signal. You've got to allow for the time delay. And you can therefore, you've got the delta range to something at a known position in space and delta velocity to a known velocity object. And you can fuse those into separate observations.
Right.
So essentially, it takes the Kalman filtering that's done inside the GPS module, but we do it inside our ArduPilot, but combine it with the inertial data.
Right.
Intermediate step would be to just get the covariance matrix out of the GPS unit and use the covariance matrix in your fusion.
Yes, yeah, if it's a GPS that makes that available. Yeah,
It still loses information though.
that's true.
So can we now merge our high sensitivity accelerometers with the high range accelerometer in the same EKF? So
Yeah.
like merge we have the 30G now, right? And merge that with the data that is coming.
Yeah. Okay, so the question is, can we take a high range accelerometer and a low range and merge that data? Now, you wouldn't take them into separate observations. The EKF doesn't handle an IMU as an observation. It handles it as it uses it for the prediction.
So we'll have to do it at the
You merge those two bits of data before it went into the EKF.
So you run that as a separate EKF.
You wouldn't do that. You would basically have a very simple algorithm that if the low range data if the low range sensor saturated, you use the high range sensor, and it would just get you out of
So, with more computing power available on the S7 series, is there a thought of changing over to a UKF?
Okay, so the question is, extra processing power, should we change over to a UKF?
we need it.
My thoughts at the moment are that if we did that, we would give up the ability to run multiple lanes and the type of voting thing that we're talking about moving to. So now,
Because of computational limitations? Or?
yeah, computational limitations. My experience with the UKF, and I have actually done a version of the EKF 3 maths base states as a UKF written in C code for a client, and they wanted to do the MATLAB study first, and then went all the way through to the implementation on the C code. Actually, was able to fly it on a Linux-based computer. The end result, it wasn't pursued any further as a project because it gave a performance improvement, an accuracy improvement, but it was pretty modest. Like, it was hard. You had to be pretty experienced to be able to look at the two curves back to back and say, well, that's better. And there was some improvement, but it used about 5 times more processing.
So we have 5 times more processing.
Well, you do, and that's exactly it. But if you did that, then you won't get your redundancy. And I'd rather have the
but
redundancy.
you've got 3 EKFs running at the moment. You said we've got 5 times more processing. So you can run 3 UKFs to do the same.
Well, you could run one UKF.
Yeah.
But do you want to give a quick summary of what actually a UKF is versus?
Okay. So you. Okay. I won't use the black pen this time.
Try to get away.
All right. So we have. I've got a variable. I don't know. Let's call it my height. So variable height, and I make an assumption about this is what I think my height is. Here, that's my expected value. But we know it's not there. It's somehow we represent it in the extended Kalman fluid formulation. We represent height as a statistical quantity with an expected value and a statistical distribution defined by a normal distribution with plus or minus 1 sigma. So that's plus 1 sigma and minus 1 sigma. Statistics, apologies for those that haven't covered statistics in the past. The EKF makes an assumption that all the operations, essentially the operations that are used to propagate things forward in time are all linear, and it uses that to reduce the number of computations, and it assumes that all the distributions look like that. So essentially what you carry around in the EKF is a state vector which contains the expected value, and the covariance matrix which contains the information for each state about where essentially what that 1 sigma value, what that distribution is. What you do with the UKF is you still make an assumption about errors, but what you do when you're trying to take, so this is my error distribution at this point in time. Now I'm going to do some mathematical operations using this height, and it's going to be predicted forward in time. And after I've predicted it forward in time, it's going to have a different error distribution. It might look like that, or it might look like that after you predicted it forward in time. What the UKF does, I know this is the mathematicians are going to cringe here, is it essentially takes sample points, expected value point, sample point here, and these sample points represent points on the distribution curve, and it propagates those points forward in time, and thus it's able to better accommodate for operations that are non-linear. Because if you take a Gaussian, normal distribution, Gaussian distribution, and then you do a bunch of mathematical operations on it, which are non-linear, you end up with something which can be a bit sort of skewed, it's not necessarily that beautiful symmetric distribution. What the UKF does, it basically has it propagates these sample points forward. And the sample points are 2 times the 2 times the number of states plus 1. So if I've got 24 states, I've got to do 49 propagation forward through all of my equations. So it's expensive from that point of view, but it's got some benefits when you start to get to larger errors and certain types of sensor observations and so on. It's not widely used in navigation filters. Usually when you're doing inertial navigation, if you're getting too far away from your expected value, you're in trouble. The EKF is more robust when you get further away, but by the time you've got further away, we handle that by resetting our states back. I know if we had no limitations on computational resources, I think it would probably be the way to do it. If you wanted to stick with, there are other types of filter options like invariant extended Cannon filters and those sorts of things.
Double precision.
Double precision enables us to go tightly coupled with EC. Tightly coupled, and it would improve the stability of the covariance matrix. So it's a good thing.
Yeah.
But the question is, any solution we do has to work on both boards, and until we end up with a variant of the EKF that only runs on an S7 or an A7 board. So we're talking about an EKF4. Yes, Jonathan.
How do you analyze those like stability margins, or how do you know how many states you can go to before you need to switch to double precision?
Experimentation. Okay. Yeah, so the question was, how do we know how many states we can add before we switch, before we run into stability problems? And unfortunately, there isn't a hard and fast rule.
What additional states would you want to add?
Okay, question, what additional states would we want to add? I would like to add a state to be able to fuse in visual odometry data that hasn't been processed using inertial data, and to actually do the scale factor estimation on that visual odometry data. At the moment, we can fuse in data from a visual inertial odometry system, but that's using IMU data. And one of the problems you end up with is that's an observation that uses inertial data to form it. We then take that measurement of position that was formed with a large contribution from inertial data, and then we fuse it into our EKF that's doing prediction with inertial data and takes this data and assumes it's an independent observation. And it's not a good way to do it. It runs into problems, particularly if the inertial odometry system starts to go into dead reckoning mode. So now I've got an EKF that's using an inertial odometry system to stop it, to prevent dead reckoning drift, and the source that's feeding it is dead reckoning. And we really need to get that scale factor into the equations.
So that's 3 states to add?
No, it's not 3 states. Well, it's a minimum one state just for the scale factor. It's really, the visual odometry system will have these arbitrary length units, right? Now, I've moved 3 length units to the right, but they're not meters. They're 3 somethings, and it's also varies depending on the distance from the objects around it. And the scale factor becomes observable as you move around through the space. I would like to see that go into any next version of the EKF. In fact, it would almost be worthwhile retrofitting it into EKF 3. This kind of thing.
How about state for depth or optical flow?
Okay, yes. So the question is, how about state for depth for optical flow? Yes, that's another nice to have. Now we're up to 26 states. This is good.
And then also, I'd like to see a separate set of position states for fusing local positioning systems like UWP.
Yeah. Okay. So yeah. So the question is, or the comment is that if fusing in something with a separate positioning system that's got its own frame of reference, might be based on the landing pad. It's a different origin. We want to fuse that in parallel with the GPS data. Then you need to estimate the offset of the reference position, the origin of that source of data relative to the origin to the GPS data, and that would require additional states. So now we're up to 29.
One more, come on.
Come on.
We have 5 times the processing power, right? We've got 130.
Yeah. And this is the thing, because CPU usage scales roughly in the order of number of states to the power of 2. So yeah, we'll need the processing power.
Fantastic. Thank you very much, Paul.